So, welcome everybody for this new seminar at the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk "To be Black or Not," given by Dr. Beatriz Bonga. And she will be properly introduced by our director, Anchon Alberdi. So please, Anchon.
Okay. Good morning to everybody, and welcome to our Severo Ochoa seminar program. And our speakers today is Beatriz Bonga. Okay, she's a theoretical physicist with a strong background in general relativity. Her current research focuses on foundational questions in general relativity and predictions also for future gravitational wave observatories such as the Einstein Observatory and LISA. Currently, she works as assistant professor at the Radboud University in the Netherlands, and previously she has been working at the Perimeter Institute in Canada, Perimeter Institute for Theoretical Physics in Canada, and at the Pennsylvania State University, where she made her PhD on gravitational radiation with a positive cosmological constant under the supervision of Professor Astekar. She's author of some 30 papers published in peer-reviewed magazines. And in addition to that, and since the year 2015, she has presented 42 invited seminars and 4 colloquia, and she has given 38 presentations at conference and workshop. And what is remarkable is that 22 of them were invited. As for teaching experience, she has been lecturer at the Radboud University since the year 2021, and she has been also guest lecturer at the institutions where she was working previously at the Perimeter Institute and also at the Pennsylvania State University. Moreover, she has supervised 15 master students, and she's currently also supervising 2 PhD students. Dr. Bonga is strongly committed with outreach and diversity. And for that reason, she usually gives talks and writes articles and participates in outreach events. About her research, let me mention that she is interested, among others, in the gravitational wave theory, resonance effects in neutron stars and black hole spacetimes, and gravitational radiation in cosmological spacetimes. Today, she will give a colloquium that in principle was supposed to be black or not, but at the end I see that the title is a little bit more complete. Can we distinguish black holes from other compact objects? I'm sure it will be very interesting. Thanks a lot, Beatriz. Welcome to our institute, and the floor is yours.
Thank you very much. I don't need this. Good. Wow, that's a spectacular introduction. I don't think I've ever been introduced like that. Thank you very much. Yeah, I realize my title, "To be Black or Not," makes sense if you just talk about or think about black holes all the time like me. But if you're maybe not thinking about black holes all the time, it could maybe have come across as offensive to some. So I hope it didn't. If so, I apologize for that. Yes, so hence the new title. This is what I had in mind. Can we distinguish black holes from other compact objects? And as I said, I am wait, no, I think this needs to be removed. Yeah, now good. I am very happy to be here in this beautiful town, and also at this very fun workshop on QFTs on curved space-times, which I hope you enjoyed the previous talk by Patricia on exactly entanglement in finite regions, which is also a big interest of mine. Patricia really got me into this subject, but today in this talk, I'll talk more about my other main interest, which is general relativity. And in particular, I'm going to focus on black holes and gravitational waves. So you may, or you probably know, all of you, even if you just work on quantum field theory on curved space-time, we have lots of gravitational wave observations. We have about 100 events seen already, and as of yesterday, LIGO is taking new observations again, so soon there will be, in fact, many more. This is very exciting because this provides us with a wealth of information, right? We can learn, interesting astrophysical things like what is the distribution of black holes and their masses in our universe. We have now an independent way to go and measure the Hubble constant, which is particularly nice given this Hubble tension. And from more like the theory side, it's very interesting that we have another way of testing general relativity in a new strong field regime, a dynamical strong field regime, and we can test the nature of black holes. And all these things, they're gonna get better and better with more observations and with better detectors. And of course, since I'm based in the Netherlands, I want to show this beautiful picture of the Einstein telescope, which hopefully will be built in the Netherlands, but maybe elsewhere. But in any case, so and Lisa, right, both very cool new gravitational wave observatories. So things are really going somewhere. And in particular, in this talk, I am going to focus on testing the nature of black holes. Now, you may ask yourself the question, why would you test the nature of black holes, right? Like, are black holes a pretty established thing in physics? Which, I think nowadays they are, right? But the first people that discovered black holes, they really thought that black holes are weird. And in all honesty, I quite sympathize with them, right? Black holes are weird, right? Like, I mean, they're beautiful, nice analytic solutions to Einstein's equations, but you could have sort of said well, they're somehow too idealized, too simple. They might be nice mathematical solutions, but they don't necessarily have anything to do with physics. And you could also give some arguments, right? Because these are the only macroscopic objects that we know of that you can just describe with two parameters, right? Their mass and their spin. That's pretty weird. Like, if you want to describe me, two numbers is not gonna do it, right? Like, you can try, of course, but I'm pretty sure you can then interchange me with Bernardo and we'll be fine, right? You need more than two numbers. Black holes are even much bigger, and we just need two. So I think that is remarkable. They're vacuum solutions, which is also weird, right? Because typically when we think of stars, we think of matter, right? Like stuff there. But black holes are, well, like stars, except that they're vacuum solutions, which is strange. And connected to that, right? Because there's no matter that makes them, right? In Einstein's equations, if we just look at the relevant fundamental constants, right? We just have G and C. And there's no matter length scale or anything, right? We just have G and C, which also means, right, that if, at least in 4 dimensions, with G and C, you cannot create a length scale. And as a result of that, that mass parameter in your, say, Schwarzschild solution is really, truly a free parameter. Means can take on any values. This is also the reason why we seem to have black holes on all scales, right? We have stellar mass black holes and supermassive black holes that are millions or even billions times more massive than the mass of our sun. We don't have any other star-like objects or things like that that really span this massive range of scales. Good. So, I think black holes are weird, so it seems reasonable to go and really test whether they're up there in our universe. It's okay. How do we do that? Well, the astrophysicists in this room and elsewhere do that by essentially testing this thing, that there's a lot of mass in a small region. So how do they do that? Well, for instance, if we look at the center of our own galaxy, we can see a bunch of stars. And based on the orbit of these stars, we have to conclude that there has to be a lot of mass. And it has to be, of course, within the smallest orbit of one of the stars. And then you say, well, then it might as well all be within the Schwarzschild radius, and hence there is a black hole. But of course, this is not a very good test of really it being there, being a black hole. It just tells us that there's a lot of mass in a somewhat small region, but doesn't quite test whether this is a black hole. Similarly, for tidal disruption events where black hole-like objects eat stars, we can learn a lot of things. It's plausible that they're black holes, but we're not quite really testing things like, is there a horizon, etc. I think one of the best evidence for the existence of black holes are these recent pictures by the Event Horizon Telescope that measure the X-ray emission from accretion disks. But also in that case, I mean, they're beautiful results, let me be honest, but even in that case, really to interpret the data, there's a lot of astrophysics that goes into the interpretation. So it's not that clear cut. This is all in the electromagnetic spectrum. Then as of 2015, we now also have gravitational waves, which allow us to have a new way of trying to test the nature of black holes. And that is what I'm going to focus on in this talk. Now, how to test the nature of black holes? I think there's sort of two key tests that you can do, right? You can do consistency checks, where you say, okay, I'm going to do multiple measurements of this object in the sky, and I'm going to make sure that all the properties that I see of this object are consistent with it being a black hole. Or I look at my data and I say, okay, is this data, can I describe it with a black hole and with some alternative model, and which of the two does better? So if the first set of consistency checks, we have black hole spectroscopy, there's multiple moment tests, a whole bunch of other things. I'll get to these later. And then for the alternative models, you can compare different types of models, right? So we have standard other compact objects like neutron stars. So you can ask yourself the question, is this, the gravitational waves coming from this object? Can I also describe it with, say, a neutron star instead of a black hole? Or you could have, say, a black hole in some modified theory of gravity, right? Say quadratic gravity, and see if it fits the data. Or you can have, standard GR, but, somewhat exotic or atypical new matter, not like a neutron star or something like that, and see if those objects that you can create that look like black holes fit the data well. And in the rest of this talk, I am going to first talk about these new matter models and new atypical matter models and contrast them with black holes. Then in the second part, I'll talk a little bit about black hole spectroscopy. And in the last part, I'll talk about this. So the good news, if you're a quantum field theorist and you got lost in any of these parts, most likely you will be able to catch up in the new part because it will be all new. So don't worry, not all of your hour will be wasted. In any case, so the first part, right? So these new matter models, or typically these things go by the name of exotic compact objects or black hole mimickers. And we have essentially two sort of rough categories. So we have black hole objects or mimickers that have smooth distributions, and those that have a very clear-cut, well-defined boundary. Now, the smooth distributions are such that there's no horizon, but they're quite nice in the sense that their formation scenario is very well understood. So we can, for these kind of objects, really can simulate them on the computer, right? We don't have the object. We put some initial conditions with, say, some scalar fields, things like that. We let it evolve. We see these objects form, right? Like we really understand sort of how, in principle, in nature, they could form. And examples are, for instance, boson stars. So just to give you an idea, right? This would be, say, some scalar field that has some density profile, and in principle, that density profile, it has some tails. So, in principle, it goes all the way, it's non-zero all the way up until infinity. Hence, the fact that they don't really have a boundary. So typically, of course, if we talk about these objects, we say they have a radius, but by their radius is simply defined as, say 95% of the mass is within this region, and that's the radius. But in principle, they extend all the way to infinity. But, these are, as I said, like their formation scenarios is nicely understood. It's might be plausible, right? Like we have scalar fields in our universe, so it's maybe not crazy that we have objects like this. And the other class with a boundary is typically the situation where we sort of glue two space-time regions. So we say, well, these should be black hole mimickers after all. So, let's think about the non-rotating case. So on the outside, it should be like Schwarzschild. So let's just pick the Schwarzschild space-time. And then on the inside, I don't like it that it's a vacuum solution, so I put stuff in there, say. And then, of course, right, you can always glue solutions in the Einstein field equations. Just the price you have to pay is that you get a membrane at the intersection. And that's indeed what you have here. And the thing, of course, it's, the nice thing about this construction is quite easy to write down theoretically. The only part is that their formations, or the formation scenario of these things, is very poorly understood. It's strange to somehow create these kind of objects. And examples are firewalls, certain wormhole models, and gravastars and anti-de Sitter bubbles. So then one key thing that all of these black hole mimickers should do is that, right, they should mimic, or they should at least satisfy this astrophysical definition, so to say, of lots of mass in a small region, right? Because we have quite some tests about that. So that lots of mass in a small region, we can quantify by their compactness. So we look at the mass over its radius. And for a non-rotating black hole, that number is 1/2. For the next most compact object in our universe that we know of, we're quite certain that are there, neutron stars, and they, can have compactness up to about 0.2. The next object, right, is already, 1,000 times less compact than a black hole. Those are white dwarfs. And then just, for reference, say if we look at our sun, it's very small compared. It's not that compact at all. Good. So of these black hole mimickers, these smooth distributions, their compactness, of course, you have a bunch of free parameters that you can work with. Right? If you have a scalar field, you can introduce some self interactions, whatever. So you have quite some wiggle room to play with. But even, whatever you do, it turns out that it's almost impossible to go beyond this compactness of 0.3. So you don't really get that close to that half of a non-rotating black hole. These spacetimes with a boundary, you can essentially make them as compact as you like, right? Well, of course, not less than 1/2, because then you would collapse to a black hole, but you can make them pretty much to 1/2 plus epsilon. Yes. There is no theorem that will show you that, but there's lots of theoretical constructions, and people have really sort of been fine-tuning and things like that, and they don't find any configuration higher than this. So there's not a theorem, but whatever you try to do, like all the natural or most plausible things have already been tried. Yeah. Thanks for your question. Yeah, more, please. Great. Yes, please. By the way, I didn't say that, but questions are always welcome.
Could you wait, please, so that?
Oh, but yes, please wait for the microphone.
So what's the difference between the width boundary black hole mimickers and black hole? Do you mean just is there a singularity or not?
So yeah, and none of these, well, typically none of these things have a singularity, right? These smooth distributions don't even have an horizon, but from an observational standpoint, right, on the outside they look quite like black holes, but they're not, right? Either because indeed they don't have a singularity, they don't have a horizon, things like that. Yeah.
Okay, so with the width boundary could have exact compactness as black hole. It's just without singularity.
Correct. Yes. Like questions, right?
Thank you so much for taking questions. So how is following up on this, right? What do you call a black hole versus black hole mimickers? For example, you have a trapped surface for a long time. I would call it black hole still. So is the singularity what you would call black hole or not? Or singularity?
Okay, so for the purpose of this talk, I'll be very conservative and, well, call anything that is like Schwarzschild or Kerr, I should say, for a long time, that I'll consider a black hole. So
a trapped surface for a long.
That is, yeah, I would, yes. Yeah.
Maybe we can reserve the technical talks to the end, if that's okay. So,
Sorry, yes.
sorry. Thank you.
Very technical questions, maybe you need to say, but good. So for the rest of this first part, I'll focus on this class of spacetimes with these boundaries, just because their compactness can be really like a black hole, so they're kind of an interesting class, I would say. So as I said, right, the examples are gravastars and certain wormhole models. This is an artistic picture of a gravastar, but for the people that don't know what it is, essentially what you have on the inside is dark energy, or if you want, a de Sitter universe. And then on the outside, it's just Schwarzschild, and then you have a membrane across it. Now, before, of course, you go and do lots of spend a lot of computational energy and data analysis time and hours on actually comparing your data with these models, of course, you should do some theoretical tests, I would say, make sure that these objects that you're looking at are in fact actually stable. Because if they're not stable, right, they might not even be there in our universe. So what's the point? So that's what we did. So we looked at perturbations of these kind of objects in the small wavelength limit. So we introduced some radial perturbation for these objects, right? And we asked ourselves the question, okay, what is going to happen with this perturbation? Is it going to grow or going to decay? So let's zoom in. So if we zoom in, right, we can say, well, we're looking at the small wavelength limit anyhow, so we can just consider it to be flat. And we look at these radial perturbations. So that means just perturbations in the z direction, so to say. And we did our analysis for the case where you just have an interior vacuum. So this does include things with a cosmological constant or not. So it could be indeed like a gravastar. And on the outside, we have the Schwarzschild exterior. And our analysis, what we decided to do is just, we did this in full nonlinear, full linear general relativity, or we linearized this. But we did this, of course, in general relativity and asked ourselves the question, what's going to happen with these perturbations? Since those calculations look kind of ugly, I decided to present you the Newtonian case, just because it is, the whole principle is completely, one-to-one. You can map the both cases, but you can upgrade my Newtonian analysis to the GR case. I just want you to know that. Good. So let's look at the Newtonian case. So instead of working with Einstein's equations and the conservation of your stress energy tensor, you now work with the continuity equation, the momentum equation, and the Poisson equation. And then putting those together, you find this particular formula. What is this formula? Well, this formula tells us how this perturbation will change in time, depending on the perturbations of your potential, your gravitational potential, and the disk forces, so to say. So in particular, right here we have our gravitational potential, which just satisfies, this Laplace equation with this boundary condition, right? This sigma is the surface energy density of my membrane, and we have some disk forces, and these disk forces come essentially from the fact that, well, you work with a membrane which has some internal energy density and pressure, so that naturally wants to do stuff, so to say, to these perturbations. And let's see what it will want to do, right? Will it want to make the perturbation grow, or does the gravitational force, will the gravitational force dampen this perturbation? Good. Now, I am, as I said, right, I'm only interested in perturbations that are orthogonal to the membrane. So these lines with a, what's it? Okay, the vertical lines, right? These are derivatives along the horizontal direction, so we don't need to consider those, right? We're just going to look at stuff in the z direction, so we can ignore this term. And now we need to look at the disk in force, where also, again, we can ignore this term, and the disk out force, where we have all these terms. Now, these terms, right, if you're very good at Newtonian physics, you see them very nicely. I am no longer good at Newtonian physics because it's been a long time. So actually, I derived this starting from GR and take the Newtonian limits, which is pretty terrible. But yeah, once upon a time, I was in a class, someone said like, yeah, if you don't know the classical result, just, do the quantum calculation, take the limit h bar to 0. And I was just laughing. I thought, what an idiot. And now, many years later, I sort of find myself doing the same thing, but in the GR sector. In any case, these are these disk forces. So, and the question now is, right, like what happens in this eikonal limit, the small wavelength limit, right? Or in other words, the large K limit. So we need to expand our perturbations in, these e to the power I kx, and we're interested in what happens to these forces when K is large. So we'll find, in fact, that this term, it doesn't scale with K, okay, great. And this term scales linearly, or sorry, quadratically with K. And the gravitational force is just linear with K. So as you can see, right, in the small wavelength limit, this term is going to dominate the disk out force. And well, not surprisingly, in this picture, also the disk out force is the larger force. So as a result, right, you will see that this perturbation will want to grow. In other words, this thing is unstable. Of course, this does depend on the sign of your energy density and pressure. So in particular, right, you can also look at the time scale in which this this perturbation will grow, right, which is determined by this frequency. And whenever, right, the frequency is negative, you have an instability. So whenever the pressure and your energy density of the surface have the same sign, your system is unstable. So in particular, if we look at, say, as an example, the Gravistar parameter space, you see that this entire region here is completely ruled out already just from theoretical, considerations. So I think that's quite nice, which made me happy. So it made me realize, oh, maybe I don't need to invest a lot more time in these models, and I can just start with investigate other interesting models. In particular, I wanted to mention this. I think this is kind of nice for people that know about tidal love numbers. If you don't know about this, you can forget this comment. But tidal love numbers essentially tell you something about how easy it is to deform an object. And in particular, it turns out black holes are very rigid. So they're very hard to deform, and it means that their their tidal love numbers are 0. But typically a tidal love number is positive. But here in this case, right, we've learned that these objects, right, are unstable. So if I have small perturbation, will want to grow. In other words, it means, right, that these objects somehow prefer to be less spherical. Which means that if I look at the gravitational potential of these objects, you can, look at all the different terms. But for instance, right, you'll have a quadrupole moment squared times, 1/2 lambda, where lambda is this tidal love number. And it tells me, right, you typically want to minimize your gravitational potential. So since I want to be less spherical, right, I want to increase Q, that means that my lambda will have to be negative. So this instability is really linked with these negative love numbers. Yes. Correct. The P is the P of the membrane.
But isn't it natural that the pressure of the membrane would be negative, right? That's
so. Again, in some of these models, that's taken as the typical thing to do, but in some of these other models, it's not.
okay.
So,
but it's not impossible, right?
No, it's not impossible. No, true. So, some part of the parameter space, these models are still totally fine. That's right.
Can we leave the technical questions for the end, please, so that everything is further?
Good.
Sorry.
So this, so yes. So these models, well, at least for me, I'm quite happy to discover that they're unstable, and that's this nice link between this negativity of the love number. So just also a takeaway message: if you ever see negative love numbers, probably these objects are unstable. Good. So moving on to the second part. So if you got lost, you can wake up again. And this has to do with the 3 stages of the waveform. So you probably have seen this, but in case you haven't, right? Typically, when we look at the inspiral of 2 objects, we divide, or we get a waveform, and we divide that waveform in 3 regimes. So we say there's an inspiral regime where the 2 objects are relatively far. And in that regime, we can use post-Newtonian theory to describe the waveform. Then we have a ring down regime, which sort of happens after the 2 black holes have merged and become one. And in that regime, you typically get something that we call quasi-normal modes. So these are like the normal modes of typical objects, but quasi because they decay, right? The signal goes down. So these are called quasi-normal modes. And this regime we can describe with black hole perturbation theory, because we say, well, it's one black hole, right? And it rings down. So we might as well be able to use black hole perturbation theory. And then in the middle, we don't really have any good analytic tools. So there we use numerical relativity. And that's the regime that we call merger. Now, black hole spectroscopy that I mentioned before is done exactly in this regime, this ring down regime. Now, this ring down regime is quite interesting, right? Because in that regime, what we do is, right, we really say, okay, 2 black holes have merged into one new one. So we have one black hole. So we can use, like I said, black hole perturbation theory, which means that, you take your black hole as a background and you do linear perturbations on it. Then, of course, the question is, okay, like, when is linear perturbation theory valid? Can I, when does that start? Is that whenever, my waveform has a peak, can I use it then? Or another quantity, say psi4, when if you're a numerical relativist, that means something to you. Or maybe should I wait until there's a common apparent horizon so that I really talk about one black hole instead of like these two disconnected black holes? Or should I wait, say some 10M, this is a time unit if you're a relativist, or 20M, or like, when can I really use linear perturbation theory? In principle, like for a long time, people thought, well, obviously, you know, you should not start doing this at the peak because that is still in this merger regime, right? Like the two black holes, they've just formed maybe one common apparent horizon, but that horizon is nothing like the horizon of, you know, say a circular curved black hole, right? It's like, if you look at different simulations, it's very like peanut shaped and weird because, you know, there are two black holes making up this object. So clearly you should not trust linear perturbation theory at that stage yet. Until actually quite recently, some other people argue, well, actually, no. Somehow, miraculously, we don't know why, but you can already use linear perturbation theory at the peak. So what did they do to make that very strong claim? They did the following. They looked at some numerical simulations of black holes merging, and they started to fit these things. And what did they fit, right? So in this plot here, you see, you know, the time from the peak, and here we see something that is called the mismatch. So this mismatch is essentially, you want it to be as low as possible because that means that you have managed to fit the data very well. So the lower it is, the better. And in the data, in this case, the data, right, is that numerical simulation. So what did we fit it with? Well, we fit it with these quasi-normal modes that we obtained from linear perturbation theory. And in this case, they said, okay, well, we should first fit with the fundamental mode, right? And then, you know, if you do that, if you fit the data with a fundamental mode, you see that indeed, like before the peak, you do very poorly, right? Your mismatch is 100%. But if you go a little bit after the peak, it goes down quite rapidly, and, you know, quickly, you do quite well, you know, in order to describe the data. But they noticed something interesting. They said, well, if you don't just include the fundamental mode, but also some higher overtones, then you can even, you know, at the peak, have a mismatch that is, you know, essentially pretty much as low as your numerical noise, right? So in particular, if you include 7 overtones, you do fantastically. So this somehow seemed to suggest that linear perturbation theory does, you know, really well already in a regime where, you know, it should be very strong, you know, nothing should be more strong field gravity, I would say, than, you know, the collision of two black holes, right? So this was a very surprising result. And in fact, it was even got more surprising, I would say, because people redid this analysis not just with these gravitational waves far away at infinity, but they did this also at the horizon. And they found the same things. So in this plot, you see essentially the same thing, right? This is from the time of the peak. And you see that, okay, if you have used just one overtone, you don't do very well. But if you include multiple overtones, you do incredibly well in matching your data. So this was even more surprising, right? Because this horizon, as I said, is in the strong field regime. So, you know, these results were very strange. Luckily, there was actually a somewhat, well, maybe obvious conclusion in hindsight, but that's how it always goes, right? Whenever I fit this data with these quasi-normal modes, right, what I do, right, I say, okay, my waveform, which I denote by this H, I can fit with this model, right, where I have some 1/r term, not so important. I have my amplitude, and then my exponentials with my gravitational, or these frequencies, the quasi-normal modes, some phase, and these amplitudes. And by construction, right, all the time dependence is up here, right, in the exponential. So it means, right, these amplitudes are constant. But if you actually look at the fits that people did, right, to the data, you see that these amplitudes are not constant at all. In particular, right, if you look at the fundamental mode, right, then indeed that its amplitude is constant. But if you already look at the amplitude of the first overtone, you see that it varies almost by almost by an order of magnitude. And the higher you go, say to the third overtone, you see that you vary like more than 6 orders of magnitude. So the conclusion was, okay, well, maybe you thought linear perturbation theory did wonderful, but in fact, what you did is just overfitting. So there was nothing fundamental, right? It's GR is still a proper nonlinear theory, luckily, and linear theory is sometimes great, but not all the way until this very dynamical regime. So the nice thing is, in fact, that what people then did, they said, okay, well, actually, can we maybe do better then? Because it was, at least from a data science perspective, it was kind of nice if we could fit more tones, we can do better black hole spectroscopy, right? Because the more tones you have, sort of like the more measurements of your black hole and the more consistency checks you can do. So what people then did, they said, okay, well, we're going to do the same sort of exercise. We're going to go fit the data with multiple overtones, but not crazy many, like 7, because clearly then, you're overfitting. But let's do something slightly more agnostic. So in this case, what they did is they fitted the data with the fundamental tone, 1 overtone, and then they said, okay, we'll let the data choose where, what the best next frequency is. And that's what you see here in this plot. So in this plot, you see the frequency, which on this axis, you see the real part in there, the imaginary part. Of course, these frequencies have an imaginary part because they're quasi-normal modes. So you need a decay. Therefore, we have an imaginary component. And here we see this mismatch, right? And as you remember, right, we want the mismatch to be as low as possible. So what it seems to suggest, right, the data really likes to have a frequency that's in this area. And if you look in this area, you see that that frequency corresponds exactly to the prediction you would get from not using linear perturbation theory, but going to the next order in perturbation theory. So from quadratic perturbation theory, so to say. And in particular, right, this would have been the next overtone, and that's up there. So that really tells us that, in fact, luckily, GR still is a nonlinear theory. And even if you want to go and look for extra overtones, you need to include at least, or need to go to higher order in perturbation theory. So there are nonlinearities in the data. And this is quite exciting because hopefully, well, not soon, but in the next years, we can actually go and measure these things. So we can sort of see these nonlinearities in our gravitational waveforms. Now, what we also then decided to do is, okay, somehow let's go and look in this very strong field regime, right? Because there, it should have been very obvious to somehow get these quadratic modes, right? Because the strong field regime, there, GR should be even more nonlinear, so to say, so we should find them. So what we did is we looked at the numerical simulation of the head-on collision of 2 black holes. And we did the same analysis as the other people that did that at infinity with our gravitational waveforms. So we fitted the fundamental mode, the first overtone, and then again, we let the data decide. And as you can see here, again, if we look at the mismatch, this is what the data seems to prefer. So it really seems to prefer, again, another quadratic mode. So that's nice. But to our surprise, it was very difficult to actually find these quadratic modes. And why was that? Well, right, these quadratic modes, if you look at the frequencies, they're kind of, well, relatively easy to calculate. But if you look at the amplitude of the quadratic modes, it is quadratic in the amplitudes of the linear modes. So if you can imagine, right, if your amplitude of your linear mode is small, then, the amplitude of the quadratic mode is going to be even smaller. So what we had to do is 2 things. We used to boost the black holes. So to maximize the linear effect, right? If you somehow boost the black holes, you get more distortions of your horizon. And we had to use very accurate numerical simulations to even find these modes in the first place. So this, I think, is kind of surprising, but luckily, we were able to find it. And we found that indeed this relation, which in principle from theory, you should be able to calculate the alpha, but that's, how it scales, that's very painful and difficult to calculate, so we didn't, but we could fit it. And we found in particular this result. So this is the slope that we got. So this is kind of nice. And I think this is exciting because this really shows us that GR is properly nonlinear, although not so nonlinear. You can still just use linear perturbation theory. You just have to go one order higher. But I think this is very exciting because it's also connects to, the next, things that we can expect from gravitational wave observations. Good. Again, if you fell asleep, you can wake up again. Part 3. And that has to do with this question, right, that I also posed at the beginning again. So can we really distinguish black holes from other compact objects? And in particular, there's this very nice event, GW 1908-14, where we measured, or we, like, as a human species, not me, I was not involved in this analysis, that we measured this 23 solar mass black hole and some other compact object of 2.6 solar masses that we don't really know what it is. So it could be a neutron star or it could be a black hole. And then of course that's interesting, like how do we actually distinguish, these light black holes, so to say, or these heavy neutron stars, if you want, from each other? How do we do that? Well, I mean, obviously, if we have an optical counterpart, we know the answer, then it has to be a neutron star, right? But of course, if you don't see an optical counterpart, it could be either because, the objects are too far, so we can't see it with our telescopes, or even if it's nearby, right? It might be that the telescopes didn't point in the right direction, so you didn't see it. So if you don't see an optical counterpart, you need some other way of telling you whether this object is a black hole or a neutron star. So then we got into the business of these tidal love numbers, right? That I told you, they sort of measure how easy it is to deform these objects. And it turns out that black holes, as I said, they have a love number of exactly 0. And neutron stars have a love number typically of, say 100 to 1,000. So if you can measure, some number that's different from 0, right? That's a neutron star. But it turns out that heavy neutron stars have much smaller love numbers. So of course, then it's going to be much more difficult, right? To distinguish a small number from 0 than, a large number from 0. So that means that for these heavy neutron stars, actually, we are not, or likely we will not be able to use these tidal love numbers to tell us whether these objects are neutron stars or black holes. In particular, right, the best thing that we have so far is a measurement of these love numbers, under different assumptions where you assume that the object is highly spinning or not. And the best that we can do today is, well, not say whether it's different from 0 or not. We can only say at this stage where it was less than 800, which I mean is already great, but not so great if you want to say whether this object is a neutron star or a black hole, right? So what do we do in practice then for certain cases? Well, typically what we do is, well, if it's less than 3 solar masses, we call it a neutron star, which to some extent is reasonable, right? Because certainly above 3 solar masses, you cannot have neutron stars. We know that from, theoretical considerations and observations. So, that makes sense. Something's heavier than that should be a black hole. So we in fact actually say that everything above 5 solar masses, we call that black holes. And that is nothing fundamental. It's just something that's sort of motivated from X-ray observations, because we haven't seen any black holes with X-rays less than 5 solar masses. So we somehow say that, there are no black holes with less than 5 solar masses. This is of course strange, right? Like, I mean, we also, there could be very likely primordial black holes. These will certainly have masses less than 5 solar masses. So it's weird, right? So we, in fact, like there are many reasons to expect that you have black holes less than this. Like I said, primordial black holes, but also if I have the merger of 2 light neutron stars, I can create a black hole. And that black hole will likely have a mass less than, 5 solar masses. Or if I have some delayed supernova explosion, then I can also create black holes less than that. So to me, it seems kind of strange that, everything less than 3 solar masses we call a neutron star, but that's in practice how we've been sort of operating as a community. Now, luckily, I think there's another nice way that we can do, and that is that, or tool that we can use, and that's use the spin-induced quadrupole moment. So what's that? Right? If an object is spinning very rapidly, it will want to deform, right? It will not stay spherical, right? We know, like the Kerr solution, right? It's not a spherical solution, right? It has a deformed horizon. So similarly for other objects, if they're spinning rapidly, they get some induced quadrupole moment, and how much that object will be deformed depends on whether this object is a black hole or a neutron star again. So for instance, for a black hole, it turns out that this coefficient is exactly 1. And for neutron stars, it's larger. And the nice thing about this spin-induced quadrupole moment is that, their spin will the spin of these heavy neutron stars, which are more difficult to distinguish from the light neutron stars because we cannot use those tidal love numbers, right? The spin of these heavy neutron stars is likely high, right, to support their higher mass. And we also expect actually light black holes to be spinning somewhat rapidly. So this is going to be large, hopefully, and thus, this spin-induced quadrupole moment is going to be important. So how do we take this into account? Well, the thing is, what we need to do is create some efficient waveforms for spinning objects. And of course, we have some efficient waveforms for spinning objects, but unfortunately, we actually only have them for black hole binaries, where we always assume that this kappa thing is exactly 1, but it's not, right? So what we did is, well, we let kappa be different from 1, right? And included this effect of the spin-induced quadrupole moment. Of course, when you do that, you run into like some challenges. I'll not go into the detail, but turns out that this system of all these different, like these 9 different spins that you have, right? Or 9 different things that you need to take into account, because you have 3 spins, right? The 3 for the spin of one black hole or neutron star, 3 for the other object, and then of course the orbital angular momentum. So you have like 9 quantities that you in principle need to involve. Luckily, in these systems with black holes, you have lots of conserved quantities. So in fact, in the end, it turns out that only one object, right, one of those combinations, you really need to evolve dynamically. But if you let kappa be different from 1, turns out that one of these other things that you thought was conserved is no longer conserved. So things become more complicated, but we fixed it. I'll not go into the details, but what you then do is that you find a nice waveform model, and now you can compare the waveform models from these black holes with their neutron stars. And that's what you see here. Well, not quite the waveform. Here you see 2 important angles for the waveform. So let's focus on this plot in particular, where, well, quite ironically, the black hole case is in blue and the neutron star case is in black. Later on, I realized I should have flipped those colors. That would have made more intuitive sense. But anyhow, what you see here nicely that, well, for certain set of parameters, similar, right, to the gravitational wave events that we are interested in, if we have, kappa being 1 or kappa being, 4, it matters, right? You see that this angle really dephases, and this is something that we can see with future gravitational wave observations. In fact, well, of course, this effect also depends on the angles of your the different spins. So of course you have to be somewhat lucky that the way the spins are aligned, they should be somehow close to alignment, but not quite exactly. Then this effect is maximized. So what we decided to do, and this is still a little bit preliminary, but we did a reanalysis of this event GW 1908-14 to see if we could tell whether that extra object was a neutron star or a black hole. Unfortunately, we couldn't. But the good news is that, with the new runs of LIGO and future upgrades, we expect that this will allow us to really help distinguish these these cases where we have heavy neutron stars versus light black holes with this effect. So let me conclude. I want to say that the future is bright, I think. I think first of theoretical results are always incredibly useful, right? Before we spend lots of energy, time doing all kinds of data analysis, we should make sure that our theoretical models are sound. And in particular, I think like thin shell models, we've shown that they're generically unstable. Of course, one could fix this because, right, in the models that I did, right, I assumed vacuum or up to a cosmological constant, but I consider that vacuum, right, on the inside and Schwarzschild on the outside, right? If one were to put other stuff on the inside, then, you know, of course, that depends on the details what you put on the inside. But generically, right, for many of these models, we sort of have these vacuum models. So these thin shell models are I think, not so interesting because of their instabilities. And then I think nonlinearities in general relativity are, well, hopefully soon measurable, and I think that's quite exciting. And I think it hopefully will also inform us exactly about what goes on at the horizons of black holes, right? Because, I mean, it's fun to see gravitational waves, but they're really cool because it tells us about processes near the horizon, right? So I think that is exciting. And good. And the last thing, what I want to say is that we now have developed a new tool that will help us distinguish, you know, whether we have these heavy neutron stars or light black holes through this spin-induced quadrupole moment. Thank you for listening.
So we have now some time for questions. I will begin by asking people in the room. So if anyone has a question, and then I will let René moderate the questions in the Zoom session.
Thank you so much. That was a very interesting talk. I wonder, yeah, again, like if for example, if you had like these compact objects, right, or black holes, whatever you want to call them, and imagine that they were formed, there's some mechanism that prevents to get to those solutions that we know and love, right? Have so much symmetry, right? Matter that never quite collapses,
Yeah.
but then forms apparent horizons that last for a long, long time.
Yes.
You would expect to see maybe something in those nonlinearities, no? To see what matter is made of, no? Kind of.
Yeah, good. So
So it's a question, so I know.
No, I certainly think so. So yeah, no, I think these nonlinearities will be very helpful, particularly really to nail down exactly these more like things that really mimic black holes better and better, so to say, right? Because it ultimately from the data, right, you measure a waveform, but in the end, right, you can only measure still limited things. So the more ways we really have to get like these consistency checks, and in particular, right, something like nonlinearities, I think is a very strong consistency check. So I think this is really exciting new things that we discussed. So numerical relativity, of course, what people do is they actually do things fully non-linearly, right? So, but then of course, often the question is, okay, well, what do you do? Well, you know, on your computer, what do you measure and how do you interpret things? And in particular, for this data analysis for that last part, for the merger thing, is really only done typically using linear perturbation theory until, you know, 2 years ago.
Hi, I was just wondering about the calculations you did with those quasi-normal modes.
Yeah.
So you mentioned that you had to uncover the frequencies only in the second order perturbation theory.
Yeah.
I was just wondering what kind of masses you used for this study, and whether if you go to smaller masses where gravity is stronger on the event horizon, you will see that even second order perturbation theory breaks down.
Great. So in these cases, good. So to get the frequencies of the second order perturbation theory, you don't need to assume anything on the masses. So you can keep them in fact, right, you only have a single mass because you're still doing perturbation theory of a curved black hole, right? So you just have one mass, and then, you know, you could, and in fact, all these frequencies just keep on scaling just with the mass. So in fact, the answer for the frequencies is mass independent. Then, of course, when you go find or look for the effects in your numerical simulations, things do depend on the masses. And in this case, we used, well, in ADM units, masses similar or around 1. We haven't, That's just currently, I don't expect, it's good. So I don't expect this to be important. Let's see, good.
Maybe
At
we
least the
can.
frequencies don't change. Let me just tell you that.
Thanks.
Yeah.
Thanks. Thank you.
So any more questions? No. So if there are no more questions, Rene, are there any questions on the Zoom session?
Hi, Gerardo. No question in the Zoom, neither in the YouTube.
Okay, then we
So
can.
advanced here.
So we can thank again the speaker for this wonderful talk. So we'll be back at 3:10 for the discussion sessions.